We're going to start today by reviewing from our last lecture, net ionic equations. And so I want you to do this one on your own here. I'm going to give you a little bit of a helper and balance this out from the start so that you don't have to do it. But let's see what we remember from Wednesday. Go ahead, break this down, get it into its ionic and net ionic forms, and we'll come back in a couple minutes and talk about it. Two things that I noticed walking around. One of those things is that we have a tendency to try to normalize things in context, meaning every example we've done to this point has had some kind of solid in it. And so a number of you have been looking for, well, what is that solid? And the problem is that in this particular example, all of the substances in question are strong electrolytes. Every last one of them. Sodium chloride, strong electrolyte, completely dissolves in water. Barium hydroxide, and this is the other problem that we're running into. Barium hydroxide is a base because it's a hydroxide. We need to evaluate it based on its basic character, not on the fact that barium hydroxide does not terribly dissolve very well in water. In these kinds of conditions, we are going to assume that everything is aqueous unless we are told otherwise. Or, we identify a salt as being insoluble. So we got soluble salt in sodium chloride, strong base in barium hydroxide, strong base in sodium hydroxide, and barium chloride, which is a lot of you tried to rationalize, is that it has to be the solid. It's not. It's soluble in water too. So in this case, we have strong electrolytes across the board. And that gives us an ionic equation that shows all of those ions in solution and none of them changing. End result, this is no reaction. Nothing happened. All of the ions that were there before are there just the same after. This can happen. Again, this is why we do net ionic equations. We do net ionic equations to expose these kinds of things as not being real reactions. If I just gave you that molecular equation, you'd say, oh, okay, chemical reaction occurred. Truth is, nothing happened. I put those two things together, I will get no evidence of a chemical reaction whatsoever. No heat, no light, no solid, no gas, no anything. And the net ionic equation tells me why. Now, it's also possible that you can have a chemical reaction where the net ionic equation and the total ionic equation are identical to each other. Think about the lab that you did this week. You had the barium hydroxide reacting with the sulfuric acid. So we had an acid-base neutralization reaction that made an insoluble solid, barium sulfate, and water. Strong electrolytes all on that left side of the reaction. Non-electrolytes on the right-hand side. Everything changed. Nothing stayed the same. There were no spectator ions to cancel out. And that happens too. So just because we haven't done an example like that yet doesn't mean that it's impossible. Don't go searching for things that aren't there. It's entirely possible. Trust your solubility rules. Trust your instincts about acids and bases. Don't go looking for things because you have to assume that, well, I wouldn't have given them a reaction that didn't have an actual equation, would I? Sometimes there's a point. This happens to be that point. So the other thing that we need to do in review, this is review of your post-lecture from last night, is talking about oxidation numbers. Now, if you haven't done the post-lecture yet, we can pretty much distill that activity down to two basic fundamentals. Sum of the oxidation numbers equals the charge. And certain elements have known charges associated with them. So fluorine is always -1. Oxygen is almost always -2. Hydrogen is either +1 if it's with nonmetals, which is usually the case, or -1 when it is with metals. Everything else that we can kind of come up with can fall back to one of these two guidelines if we follow our algebraic steps correctly. And so we'll just kind of do a couple of examples here with that, just to kind of get everybody on the same page. So the first examples, we can prove to ourselves that oxygen is -2 and sulfur is +4 in sulfur dioxide. How that comes about is algebraically. If I think of a chemical formula like an algebra problem, I would end up with something like this. The oxidation number of sulfur plus 2 times the oxidation number of oxygen gives me 0. Since oxygen is actually -2, I can work out the algebra here. S minus 4 is equal to 0, so S must be +4. I can work out a similar kind of example with the chromate ion. The oxidation number of chromium plus 4 times the oxidation number of oxygen gives me -2, because that's the charge on chromate. Since oxygen is -2 in charge, chromium -8 gives me -2. Chromium must be +6. So this is pretty basic algebra. Anyone in this class at this point in time should be able to handle it relatively easily. Again, if they follow the guidelines. Now, if you just start guessing, it becomes a lot more difficult. Or if you start looking at the periodic table and saying things like, well, phosphorus is in group 15, so it should be -3. That doesn't work most of the time either. Almost all the time that we're dealing with oxidation numbers, we're usually dealing with hydrogen and oxygen compounds. And so to that end, we're going to see that oxygen and hydrogen rule used a lot. What do I do with something like Cl2 though? What's the oxidation state of the chlorine? Well, total charge on Cl2 is 0. I could do the algebra. 2 times chlorine is equal to 0. So chlorine must be equal to 0 as well. I could go that direction. anytime I have multiple atoms of a given element, the thing I need to recognize is that those atoms are all going to have the same oxidation number. So all of the fluorines in sulfur hexafluoride are all going to be -1. And if I know that, then it's pretty easy to rationalize how the sulfur is +6 to balance it out. In the case of elements, even molecular elements like chlorine, like oxygen, like tetraphosphorus, like sulfur 8, if it's in an elemental state, even a molecular elemental state, its charge is 0, which means its oxidation number is 0 also. But with the same logic in tow, I can make relatively simple kinds of observations, knowing that every single element of a particular kind is going to have the same oxidation number. So in the case of ammonia, I've got 3 hydrogens. Each hydrogen is a +1, which makes a total of +3. The nitrogen is going to have to be -3 to balance it out. Take a minute and try to do the chlorate ion here on your own. ClO3. So what is chlorine? What is oxygen? Let's take about 90 seconds and try to figure that one out, if you haven't already. All right, how do we do? Oxygen should have been -2 because oxygen's almost always -2. Really, the only time that oxygen isn't -2, there's 2 exceptions. If it's with fluorine, like in OF2, the electronegativity of fluorine supersedes oxygen. And so oxygen actually takes on a +2 state there. It's very rare. Or peroxide ion. Peroxide ion, you've got 2 oxygens sharing a -2 charge. So each one's on a -1. It's also why peroxides are really reactive, because oxygen is in an abnormal state. Oxygen would rather be -2. In peroxide, it's only -1. So it ends up reacting to get back to -2. Okay, so this is what you had to do last night. Now we go about using it. And what we understand is that we're dealing with a different type of chemical reaction here. In particular, we're dealing with a type of reaction where electrons are being transferred from one element to another. Now, we've seen other examples of this in the past, but we've never really called it redox before. We've always called it something else. Combustion, decomposition, combination reactions, single replacement reactions. Truth be told, though, they are different. And they all have this common theme, the movement of electrons. Why we do all that stuff with oxidation numbers is so that we can accurately track how those electrons are moving around. So with an oxidation number, I can look at this reaction between zinc and copper and see that zinc started at a 0 state and ended at a +2 state. Well, to go from 0 to +2, it had to have lost 2 electrons along the way. I can see that the copper went from a +2 state to a 0 state, meaning it had to have gained 2 electrons along the way. Now, how did it get those 2 electrons? The zinc gave it to them. Or the copper took it from the zinc, however you want to look at it. These processes occur simultaneously. Oxidation is always coupled with reduction. That's why they carry the name oxidation reduction reactions, or redox for short. Now, a couple of things I want you to notice about this equation also. By this point, you should recognize that it is impossible for us to get an ion like copper 2 without doing some kind of aqueous solution making of some sort. And even the reaction itself tells us that it's aqueous. It's dissolved in water. Notice what's missing, though. How did we get to copper 2? Is it copper 2 acetate? Is it copper 2 sulfate? Is it copper 2 chloride? Is it copper 2 bromate? Does it matter? In this case, no. Whatever that anion is that delivered the copper to the water, it's a spectator. Redox reactions are almost always in net ionic form. Why are they almost always in net ionic form? To get rid of the extra, to give us the purest idea of what's going on inside of that reaction. Spectator ions have no place in redox reactions because they just cloud things up. They just make things more complicated than they are. Other thing I want you to notice, there is a relationship between the term oxidation and oxidizing agent, the term reduction and the term reducing agent. And notice they're not talking about the same thing. The oxidizing agent is not referring to the thing that is oxidized. Rather, the oxidizing agent is the other reactant, the one that is causing oxidation to occur in the other substance. And the reduction is not occurring in the reducing agent. The reduction is occurring as a result of being introduced to the reducing agent. There's kind of a flip-flop relationship, a crisscross relationship here. Oxidation and reducing agent have a lot in common. In fact, the reducing agent contains the element that ends up getting oxidized. And the oxidizing agent contains the element that ends up getting reduced. But they're not the same things. Let's put some terms to this. Let's put some definitions to this. The term oxidizing agent refers to a chemical substance, a reactant, that forces the oxidation of another reactant. In turn, let's add something to this. And elements in this substance will be reduced. The oxidizing agent itself as a whole doesn't get reduced. One of the elements that make up that oxidizing agent get reduced. Same thing for reducing agent. A reducing agent is a chemical substance, a reactant that forces the reduction of another reactant. As a result of the action, an element inside of that reducing agent will get oxidized. There's a central theme here that I want to make sure that we understand before we move on and move off of this. Elements get oxidized and reduced. Individual elements get oxidized and reduced. Reactants, those are your oxidizing agents and your reducing agents. It is very easy to get them confused. It is very easy to mistake them for one another. In particular, we're going to do an example problem next here. It's very easy to identify elements and assume that they are the oxidizing and reducing agents. And they're not. They are parts of the oxidizing and reducing agents. Let's take a look at an example. This particular chemical reaction is used by rockets to create propulsion in space. Hydrazine reacting with dinitrogen tetroxide to make nitrogen gas and water vapor. What we want to do is identify what elements are oxidized and reduced and which reactants are the oxidizing and reducing agents. Now, to do this and do it correctly, we need to identify oxidizing numbers. Our oxidation numbers, again, using our guidelines, hydrogen is going to be +1, oxygen is going to be -2, and that's going to pretty much hold consistent all the way across. In the hydrazine, we can see our equation set up there. 2 nitrogens plus 4 hydrogens, so +4 overall, are going to give us a total charge of 0. So if I do the algebra correctly there, I've got a -2 charge on that nitrogen in hydrazine. For the N2O4, 2 nitrogens -8 for the 4 oxygens is equal to 0. Each nitrogen in this case is +4. And the nitrogens in my elemental nitrogen here are all 0. So I've got an interesting kind of situation here. I've got nitrogen being oxidized on one reactant and nitrogen being reduced in another reactant. Both are ending up in the 0 state by the end. Now, this doesn't happen very often. And usually when it does, as we see in example 7, we usually get 2 different kinds of products as a result. Maybe one of them turns into nitrogen and another one turns into ammonia. But this case, that's not what happened. They all turn into elemental nitrogen. But what we can look at is what has changed. This nitrogen went from -2 to 0. It has lost negative charge, lost electrons. That's an oxidation. This nitrogen in the nitrogen tetroxide went from +4 to 0. It's gained negative charge. It's lost positive charge. It's been reduced. So as far as the elements oxidized and reduced, we've got the N. We've got the nitrogen and hydrazine being oxidized. And we've got the nitrogen in dinitrogen tetroxide being reduced. What about my oxidizing agent and my reducing agent? Well, again, it's the components. Since the nitrogen in hydrazine was oxidized, that means that hydrazine, N2H4, is the reducing agent. Since the nitrogen in dinitrogen tetroxide was reduced, that means that the dinitrogen tetroxide is the oxidizing agent. All right, any questions with regard to these terms before we move into balancing? Okay, so let's talk about balancing then. Now, as far as balancing goes, there are two different methods that we can use to balance redox reactions. And the reason for the two methodologies have to do with it's a more complicated kind of example than what we saw in before. So before, we could look at an equation like this. We look at a reaction like this and say, hey, well, you know what? That's balanced. Got one copper on each side. I've got one zinc on each side. It's good. Problem is, it's not. It's not good. Because if we look at it from an oxidation number standpoint, I can see that the zinc has lost 2 electrons in this process, whereas the copper has only gained 1 electron. If this was truly balanced, where'd that extra electron go? Zinc gives away 2 electrons and copper only takes 1 of them. Does that mean that the extra electrons just kind of floating around out there? No. It means that this reaction is not complete the way that it should be. Now, in this particular case, the fix is rather easy. We just say that the copper reaction happens twice. And so every zinc ends up reducing 2 copper atoms instead of just 1. But if we didn't know that, then we would get into a lot of trouble when it came to balancing these equations out. And that's why we focused on oxidation numbers here at the beginning. Because understanding the oxidation numbers goes a long way to helping us balance these equations. And in the first method I'm going to teach you here in class today, we're going to utilize those oxidation numbers to their maximum potential and efficiency, and use them to help us to balance the equations through a relatively straightforward albeit a little bit difficult to get used to at first kind of format. If oxidation numbers end up not being your forte, there is an alternative method. It's called the half reaction method. Half reaction method I am going to feature in a separate video as a supplemental lecture. That'll be up on YouTube and it'll be part of your assigned materials for Monday. It has some advantages too. Those of you that have to take Chem 106, you're going to end up learning the half reaction method also when it comes time to do electrochemistry. Those of you that don't have to go through Chem 106, that's, you using the half reaction method one way or another. It's really about familiarity and what you feel comfortable with. But again, I'll feature that in a separate video. Let's talk about what the oxidation number method looks like. The oxidation number method has 5 steps, and the 5 steps kind of roll off of one another. The first step is that we are going to start with a skeleton net ionic reaction where I've got 1 mole of everything. So I've got my reactants, I've got my products, I've got 1 mole of all of them. That's my starting point. That's step 1. And again, it's net ionic. So if everything's in aqueous solution, I immediately cast aside all of the spectators. Step 2 is exactly what we were just doing, assigning oxidation numbers, figuring out how electrons are moving around. In the end of that step, we are going to assign a value of delta ON, that is the change in oxidation number for each element. Now, most of the elements are not going to have a change in their oxidation number. We're really only interested in the ones that do. So we look at it and say, okay, the nitrogen went from +5 to 0. I know that that is a reduction. It went from -2 to 1. That's an oxidation. Step 3 is to use coefficients to balance those values for both processes. End goal on this one, we're going to balance everything that's not nitrogen or not oxygen, not hydrogen. Everything else is going to be balanced. So if there's chlorine present, there's going to be balance of chlorines. If there's sulfur present, we're going to see balance of sulfurs. Everything but hydrogen and oxygen are going to get balanced. In number 4, the next step, we're going to balance the overall charge. And this is where our paths start to diverge. Oxidation reduction reactions occur in solution. Almost all of them do. Some of them don't. We usually have other names for those, like combustion or decomposition or others. But for the ones that do, we need to know what kind of environment they exist in. Are they in an acidic environment where there's lots of H+ ions present? Or are they in a basic environment where there's lots of hydroxide ions present? The answer to that question is going to impact the balancing process. And so step 4, we're looking to balance the overall charge of the equation using hydrogen ions if it's acidic, hydroxide ions if it's basic. And then the last step, balancing hydrogen and oxygen using water. This usually piggybacks right off of step 4. In a lot of cases, there aren't a lot of hydrogens in the molecule. And so based upon the number of hydrogens or hydroxides that you add, you usually end up adding a similar number of water molecules to the opposite side to balance it out. And that's the process. Not many steps, pretty methodical, but you got to know what you're doing. And you got to know what steps to take. And the only way to do that is practice. And guess what? That's what Monday is all about. Whole point of Monday is to give us just about as much practice as we can stand. Now, I don't have enough time to do example 7, which is what I would have done this morning. Example 6 only requires a couple of steps, so we can go through it, but it's not going to be as instructive here. If I had my reaction in example 6 here, I would see that I'm starting with iron in the solid phase, reacting with palladium +2 in the aqueous phase, and it's turning into palladium metal and iron 3+ aqueous. So that's my step 1. Step 1 complete. I've got my net ionic skeleton reaction, one of each of everything. My second step is to assign oxidation numbers. Oxidation numbers I'm going to put here in blue. Iron as an element is going to be 0. Palladium is going to be +2 because that's its charge. Palladium metal is going to be 0. Iron is going to be +3. To assign those delta ONs, those changes in oxidation number, I've got to pair together the two sets of terms that there are the most alike. So in this case, I'm going to pair together the iron and the iron 3+ because they are the most alike, and the palladium 2 and palladium metal because those are the most alike. In cases like example 7, we're going to use similar kinds of logic there as well, where the perchlorate and chlorite end up getting paired together because they are the most alike, and the chloride and the chlorine get paired together because they are the most alike. That'll be an example that shows up in the videos for Monday. But wanted to show you that the logic is the same there. In the iron, I'm going from a 0 state to a +3 state. That's a 3-electron process. In the palladium, I'm going from a +2 state to a 0 state. That's a 2-electron process. If these numbers are equal, then all I would have to do is move on to the next step. Since they are not, I need to use coefficients to get me to that spot. What's the lowest common multiple between 2 and 3? 6. So to get to 6, I have to multiply the iron equation by 2. And I would have to multiply the palladium by 3. That makes that a 6. That makes that a 6. And now, from an elemental standpoint, I have balanced out all of my palladiums and irons and the charge. This would be my balanced chemical equation. The only thing left to do is to check the charges. If I look on this side of the equation, I see I have 0 charge for the iron, 3 times +2 for the palladium, so a total charge of +6 over here. No charge on the palladium in the product side. 2 positive 3 charges for the iron. Make positive 6 as well. Since my total charges are even, I don't need to add H plus. I don't need to add OH minus. This is good exactly as it is. Steps 4 and 5 just disappear. They're done. What we'll see in subsequent examples is that that won't be the case, and we'll have to do those other kinds of manipulations with it as well. I'm going to leave it at that. Have a good weekend, and I'll see you on Wednesday.